maybe we had like not enough time. So what happened?
Yeah, I personally think the problems were on the easier side than hard, particularly hard. The
Okay,
one that took me the most time was problem 4. Aside from it, most of them were easy to do.
problem 4 about chord on a circle and tangents. This one, right? Was it about problem for this one, like on the extension of chord KL of a
Yes,
circle?
yes.
Uh-huh. Okay. Okay. Okay, let's try to do this class in a sort more practical than previous one. Um, and try to like I like doing and having different types of classes because normally there would be advantages and disadvantages in any format, right? So just alternating the formats, we can get use of like many of them. Uh, so today I would like to tell more solutions. So let's like jump immediately to the solving process, like not solving, but discussing and consideration process. So one sec. Can you see the demonstration? Like the notebook?
Yeah, but blank at the moment.
Yeah, just one sec, trying to understand why everything is so slow. Okay, so the first problem of the previous class, of the previous task, was very technical, though I believe it's one of very useful. So me personally, I was using it quite frequently. Sorry guys, like the system is misbehaving. Let me just reload the my laptop. Just unbearable. Just several like, more minutes. I will reload. So as to the problem, problem number one, problem number one, it was missing some additional conditions actually, and sometimes um, you should study these corner cases. What's happening? Yeah, hopefully now you should be able to see everything, right? Demonstration task. So this is actually technical condition, and of course a technical additional restriction is needed here. Otherwise, like there would be some exceptions, probably even very serious exceptions. So a plus b is normally less than 180 degrees. But basically, that is when you have like what you have if you have geometrical interpretation of the condition, of the geometrical part of the condition. So you have an angle. A, O, B, and it is divided into two parts. Here, of course, it's supposed to be greater than 0. And alpha and beta would be greater or equal than 0. And we have this part, so this angle is alpha, this angle is beta. And actually there are many technical options how to prove this directly. So in particular, we can study the function like denote the total of these two angles as gamma, which would be constant, and consider this ratio sine A to over sine gamma minus A. And study this. Actually, I don't remember. Probably this may be true even for broader angle than 180, but I just always used this technical lemma for this range. But we will prove this in a slightly different way. I will try to do the proof a bit more geometrical. I will do following. Instead of studying just angles, and considering this as just a function over the angles, I will try to consider this as a like geometrical how it's like situation. We say etude. Yeah, Karam writes that this will work for a greater than a plus b greater than 180 as well. So seems like we can then consider a plus b being just from 0 to double pi to 360. But once again, the most reasonable cases would be normally in these ranges. So we may consider this point as soon as we construct these. So first we will take some particular points on the sides of the angle, and also we will consider the auxiliary point x here. So from this point of view, we already have a problem which is divided not just for angles, but it's divided for the entire geometrical situation, which includes the triangle. And I will actually use another statement, which I used even more frequently. And the statement is following. So this I consider being a very useful lemma as well. So if we have here a, b, x, and this, or maybe, yeah, let it be a, b, x, and here would be point y. This angle would be phi. This angle would be psi. Then let me recolor these elements. So these would be red. These would be blue. Then ratio of these two segments, AY over YB, so the red one to the blue one, would be calculated quite easily by the following formula. It would be equal to AX times sine phi phi. I think it's phi, right? Times sine phi over bx times sine c. So if we consider these elements, then the ratio on the opposite side would be easily calculated with this formula. Why it's true? Like the proof of this lemma is very straightforward. It could be proved either by sign theorem or by expressing the area of the triangle. So AY would be equal over YB would be equal to, by famous statement, it's equal to ratio of the areas of the triangles, AXY or BXY, because they share the same height. But this would be expressed then through the sine functions, AX times XY times sine p over bx times xy times sine c. So we just cancel out one common factor and we get immediately the formula. So I believe like almost every Olympiad I used this lemma. It was my main technical trick, this trigonometrical counting. And this would be one of the most, like for me, this would be one of the most useful statements there. So if we apply that to this situation, we may write down this ratio ax over bx would be equal to something quite understandable, right? Ax over bx would be exactly expressed through the sides, like lateral sides, and the pieces of the angle which was shared into two, or which was cut into two pieces. So it would be AO times sine alpha over BO times sine beta, which is technically just some constant ratio times sine alpha over sine beta, which we can reverse, of course. We can rewrite this as sine alpha over sine beta equals to BO over AO times AX over BX, where once again, this ray itself and correspondingly the point X, we can move them. And the rest of the construction is just fixed part of the construction. So this fraction is constant, and this ratio depends on the choice of the ray X. So we also may denote these as blue because they also would be changeable or changing the ray. So these changes on this side, these changes on this side, so we can just see that if we define uniquely this ratio, and of course if the sum of the angles alpha plus beta is defined and fixed, then we have that AX over BX is also defined and fixed. So we sort of translate this problem to the language of similar statements about the segments. So the statement becomes equivalent to the statement about the segments AX plus BX equals to AB. And X is the internal point. Like maybe not internal, but it belongs to the segment. It may be either internal point or the end point of the segment. And also we know that AX over BX is given, right? Is provided. But this becomes like very obvious statement. So it becomes like I would say very well-known statement. So generally, if we consider this straight line AB, there would be in principle just 2 points which have the same ratio AX over BX. And just one of them would be such point that X is the point of the segment AB. So that would be related to the topic of Apollonius circle, quite famous theory. So we may finish at this point probably, but also like if it's not enough, like in most occasions, probably this would be considered as something which is enough, because this would be rather more popular situation, more well-known situation than this one. But we can still continue by considering the straight line or over the straight line. So we can consider the function, say, AB minus BX over BX, which would be AB, the fixed segment over BX minus 1. So here we have just one parameter which is changing, the denominator BX. And if we have some particular value, R, then we can see that this is just solvable over BX. Yeah. So that is it. So this equation, it produces just unique, like maybe some details should be then considered, because we can construct a segment in two directions on the straight line from the given point, and also the condition that X is the intermediate point should be fulfilled here and double checked here. But first of all, even this part, it was already more or less clear. But if we want to be to give like perfectly full solution in some situation, we of course better do some details here, like either consider coordinates or just considering by hands the solutions BX here and considering like the limitations of that. So that is basically the principal thing. Also, speaking of the problem 2, like any questions here? Do you have any questions?
I just have a small question. In case we do the function approach, we can find the derivative and show that it's either strictly increasing or decreasing, right?
Yeah, sounds correct. So if we have, at least if we have this limitation from 0 to 180, we definitely should have very clear situation in the functional approach. If I'm not mistaken, on this, like with this limitation, it would be just strictly increasing function or decreasing, like what makes sense more. If we take alpha equal to 0, right, and go to 0 from 0 to like the full extent, it would be starting from 0 value, and the final value would be plus infinity when this is 0, and numerator is some fixed. Yeah, so I believe it probably would be just growing on this segment. Sorry, guys, just a tiny technical pause. I need to relocate to the other point, and we continue. Continue. So, speaking of problem number 2, it is actually quite an example for the previous topic of shifting a point. So, don't understand what it doesn't copy. Yeah. it is. So it is just one of the perfect examples of this technique of shifting a point when we have troubles with proving the inverse statement. So problem number 2, we had this circle. We have some hexagon. We have its main diagonals. And it should be just drawn as the statement doesn't hold. So I already made that remark previously. So I would say my approach in doing geometry would be just starting from good enough picture, and what is good enough is constructed by some reasonable guidelines, which I can describe, but not necessarily very nice. So it should be informative, and like parts of those process would be just paying respect to every single condition in the problem. In the most visual way, it's doable in doable mathematically and reasonably, and translating the properties, which we can see, to some properties of angles and equal segments. So this problem, I don't think it's quite doable, quite translatable in this manner, like I would say in very, very geometric way, though we will have many possible equalities of angles here, but still that may be not that helpful in this situation. So in this case, I would first draw the first picture. Sorry, one sec. Yep, sorry. So I would draw the first picture, then I would consider I would say more geometrical or more realizable part of this problem, because this is problem with this strange word if, which is if and if only. So that makes this technically 2 problems in one, right? Hopefully you are used to this notation. So then I would do a new drawing. So I would consider this all previous drawing and do some corrections. So here I would have first the case where we really have intersection of these diagonals. And what we need to show here is that what? Is that the statement holds for these segments, right? But that would be quite doable, because if we consider like any 2 segments here, like for example this segment, not any 2, but any 2 opposite segments, this one to this one, we may notice like we must get some use of this circle, right? Otherwise, the problem is probably not true because we can use this shifting method in slightly different way as well. So if we don't use any substantial information regarding the circle condition. So what's then? I like double checking such conditions or such assumptions because of the following thing. So imagine we don't have information about the circle. No, imagine we don't use the information about the circle. If we don't use any substantial information about circle, that technically means, like probably in a slightly philosophical way, but it then means that we act just as we didn't know that there is a circle. So just think about this. If we don't use any properties of something, we don't like we live in the same situation as if we didn't know that property. For example, if like a very clear comparison would be, imagine you have some device, say coffee machine, but you never use it. So you then live a life which is undistinguishable from the situation when you didn't have the coffee machine, right? If it's on the shelf and you never take the coffee machine from the shelf, then probably there is no difference if there is the coffee machine or there is no coffee machine. Speaking of your everyday life, this difference doesn't make any change. So this principle works perfectly for assessing some situations in mathematics and not only in mathematics. So we can easily check if it's trustful that this statement holds without the condition with the circle. So if we don't have the condition with the circle, we have just the condition about intersection of the, like we have combinatorial condition that this is hexagon. We have geometrical condition that these main diagonals, they do intersect in the same point, at the same point. We have the lengths of the segments, and basically we have nothing more. So we can check if it's like trustful that, sorry, the statement of the problem. So we may start changing some parts of the construction so that we can estimate if the property would still hold with the different positions of the possible object. So here we may consider, for example, an elongation of some diagonal, and we may consider different segments, like different couples of sides, which have the vertex on this diagonal. So this will remain part of the the main part of the geometrical construction. We will still have hexagon. We will still have the intersecting main diagonals, But also what we'll have different positions of this vertex. That means that we will have different lengths of the segments. So we will have that this F over E. So we had what? We had a question if this implies this, right? Which would be just equivalent to F over E equals to, and like what remains from this if we just bring these factors to the opposite side. So it would be B over A times D over C. But this is constant. It's not changing over these transformations. But here we have also F prime over E prime if we denote this as, if we denote this as F prime E prime, and here we will have, say, F2 primes E2 primes, then we will have that this should be equal, FE should be equal to F prime, F over E should be equal to F prime over E prime, should be equal to F double prime over E double prime. Oh, and now we have the same straight line. We have 2 points, 2 different points. We have these couples of segments, which produce us the same, like which are expected to produce the same ratio. Is it possible at all? Actually, the thing which I already mentioned, this Apollonius theorem. Let me double check that I recall this correctly in English, because in Russian it's definitely sounding like this. Окружность Аполлония. Yeah, it's called Apollonius circle. So, by the related theorem, which you may like easily find, just not to spend time now. If you like have any questions or like if you don't know this topic. So this question is about locus of such points that such ratio is fixed. So we consider 2 points on the plane, 2 different points. We consider third point, so that like if we call the first 2 points A and B and the third point X, so we consider the positions of X so that AX over BX is fixed. Exactly as we have in this problem, in this part of the problem. So we will have these 2 points. Let it be A, B, C, D, E, A, and E, so that AX over XE is fixed, and we have 3 different positions. So that theorem says that this locus is either a circle or a straight or a segment bisector if the ratio is equal to 1. So in only just case, it would be just perpendicular bisector to the segment AE. If it would be any other real ratio, then it would be just true circle. And that circle couldn't be intersected more than twice with a straight line, right? So this is not possible in principle. And like if we skip the condition about the circle, then of course we can consider infinitely many intermediate positions. So that is how we may do experimenting in geometry. So we just give up on some condition. We just forget about it for an instant of time, and we try to make some small shifts from the situation which we realize, or how we understand how we realize the situation. And we take these side steps, normally small side steps, where we can easily show that some property doesn't hold. And normally, like I wouldn't expect this to be ever mentioned in any solutions. So that is why I expect you more or less never heard such part or such consideration. And like let me know if somebody told you something like that. But I bet you at least didn't have it during like trainings, most likely, because it's not very popular for trainings. Not speaking of some open lessons and so on. Normally, teachers don't consider that they have enough time for showing this, I would say, dead ends of like thinking process, right? So when they thought of something and they came to like no result, as they will describe. But I believe that is exactly what we should or must pay much attention, because that is what actually happens like 90% of time which you spend on a competition or even during the process of solving a problem. So that is exactly what we may adjust in our practice. Not a solution of some particular problem. So that actually says like, why did I mention this? Why did I tell this story about such problem without circle? Just to emphasize that in this problem, if we don't use the condition of this hexagon being cyclic, we just cannot prove the problem or anything close to the problem. So we must somehow use the condition that this is cyclic. And of course, the most straightforward options how to use that would be by using some relations on the angles and like applying some geometry. So here I would denote some angles, which I would denote normally. So I would consider some couple, like because we have several alike situations here, I would consider one. And also I would accurately try to highlight the examples of such situation if we speak of several instances of the same situation. So we definitely have this pattern, this butterfly construction met several times here, namely 3 times here. So let's first consider one occasion, and then probably we get to the others. So I definitely wouldn't denote all the possible angles here, at least at the moment. So from this, I can definitely say that triangle ABX trivially would be similar to triangle EDX, sorry. Because that is probably the very first and sometimes the very only thing which we can notice here from the first glance. So we can notice just that we have several angles on the picture, which must be, like, some of them must be equal. We find which exactly angles on the picture are equal indeed. And that pushes us to finding this sort of similarity, either for this couple of triangles or for any other couple of opposite triangles. So if I have similarity, I do immediately or almost immediately translate that to the language of ratios, because similarity would be broken down into equalities of angles and equalities of segments, right? Equalities of angles normally come into the consideration very naturally, like here, we just noticed already that the angles are equal, but the equalities of the ratios would be some sort of hidden information. It would be not easy to notice that even if we have everything already put on the picture. So that is one of the reasons why I immediately would write down the equality. Otherwise, if I forget it in some situation, then probably I will lose the opportunity to use this part of information. And then, then it would be some consideration, like not consideration, but for me, it would be just the same as not using the circle here, right? Sometimes we may not use such condition, but that means that the condition of the problem was excessive. And that is quite a rare event, actually. So we can write down here that this equals to AX over XE, and this equals to BX over XD, right? So that's how we can extract. Similarly, we can extract the similar equalities for other segments, right? So we can say that just one thing here, it's A over D, of course. But speaking of other ratios, we can say that B over E is equal to what? To BX over FX, which is equal to CX over XE. So I literally just try to observe just these couple of triangles now at this moment. And that is how I write down this ratio. And the third, it would be C over F. C over F equals to, from these triangles, CX over AX, which is equal to DX over FX. So actually, now we need to substitute these three fractions by these ratios and check that that is equal to 1. Here it would be quite straightforward situation. So no, sorry, like not that fast. So here we first notice that we can reformulate that like the initial ratio would be A over B times C over D times E over F, which looks like Cheva something, right? Or Menilai something. And this we may reformulate as A over D times C over F times E over B, which would be exactly these three fractions. Just the second fraction, B over E, would be here in the inverse form. It would be E over B. And I believe that if we just take product of all these 6 fractions and say extract square root of that, that would be just 1 immediately without any choosing the proper fraction. Or we can choose the proper fraction as well, maybe. So I suggest you just completing the details here. So that is how the first part is solved, right? So it's 2 first part. And second part, it would be actually done by that principle of shifting an element, which we saw example of which we saw on the previous class. So we do take this picture, which is just perfect for these purposes. So suppose if A over B times C over D times E over F equals 1, then, and we want to show that then the geometrical condition holds. But what we have, what we virtually have, is that in this particular situation, it doesn't look like being satisfied. So what we do then, following thing. We, of course, try fixing the situation, fixing the construction, so that we have the situation where we do have the geometrical property. Here we can do that without big troubles. So we just adjust one of the 3 main diagonals through the intersection of other 2 diagonals. So here we technically means that we change the side lengths F and E so that the corresponding diagonal passes now through this point. But from geometrical part of the problem, from 2, 1, we have then that A over B times C over D times E prime over F prime is equal to 1, which is by condition A over B times C over D times E over F by conditions. So we have literally this E prime over F prime equal to E over F, right? And actually, this is how we can get use of that statement, which we proved as auxiliary statement. We may, of course, approach this problem directly, which actually makes not that much sense to me, but still it's also doable because we again have this we may consider this as another example of applying this statement about Apollonius circle. So we have two different points, this and this, as intersection points of Apollonius circle and this circle. But actually, this works here not that well, because two circles, they may have two intersection points, right? And that means that just by form of the statement, it sounds not that reasonable. We may, of course, apply some extended properties of a Apollonius circle. So we know that, like, we probably can handle that. But it would be already some technical operation, like to consider some more special properties of a Apollonius circle and trying to get some get used, like not to get used, but fit it to this situation without very too deep consideration. But instead of that, we may just consider the following. We may consider this angle ACD ACD, these two positions of point F. So there was position initial position of point F, there was new position of point F. And actually we can realize that this question is not about the segments. It's actually about the corresponding arcs, or in other words, about corresponding angles. Why is that? Just because AF like not about the angles, of course, it's about the sinus. So if we consider this angle phi, this angle C, then we have that AF is actually double R over oh sorry, it's just opposite. AF or sine of B equals to double R, where R is the radius of the circle. So this is just sinus theorem, the extended version. So from the triangle ACF, for example, we have that ratio AF to the sine of the opposite angle. So here it would be called just sine theorem. So we have that AF over sine of this equals to double radius of the circle of ACF, which is just technically the same circle. Same we can say about DF. So DF over sine C would be equal also to double R, which actually results in noticing that E to F equals to AF to FD, which equals to sine phi over sine C, which is equal under question mark to E prime over F prime, which would be similarly equal to sine P prime over sine C prime, which technically brings us to the exact same situation which we had in that auxiliary effect. So we have the sum of the angles being fixed. We have ratio of the angles of sinus of the angles being also same. And that actually shows, so by lemma, we have uniqueness of the position of point F, or in other terms, for this type of formulation, we have that F equals to F prime. But by lemma, the position is uniquely defined. So we have that F equals to F prime. That is how it's done. And this would be very, very uniform, very popular technique. Okay, what's next? The problem number 4 was mentioned, right? Like, any questions so far? Questions, comments? Okay. How are you guys? Are you following?
Yeah.
Okay.
I'm following.
Okay. That's good. Then let's consider this, and then we say several words about a new thing, and basically that will be the end of the class. So first, a good picture, of course. So problem number 4, on the extension of chord KL of a circle with center O. So we need a circle. Like in such tradition, we always start from a circle. Then we need to take chord. So we have the center O. Then we have the chord and the extension. Sorry. So like I first read the entire sentence. So on the extent I understand that I cannot read the entire thing. Like I cannot recall the problem by the first lines. Like just too many geometries start very similarly to this. So we have this chord KL, and I don't understand that I don't remember. Like I don't understand what should I expect to be drawing. So I read and reread the same sentence a couple of times. So we'll have an extension of this chord of a circle. A point is A is taken. Some point A should be located then, and from E2 tangents AP and AQ are drawn to the circle. So we will have tangent lines passing through the point A. So A is definitely the external point somewhere over here, and it would be on the extension of KL. So seems like the extension here would be meaning that extension outside of the circle, right? So like, maybe it's obvious, but it's also the main emphasis, because like we need to get some external point to get some tangent lines. So seems like we need to have situation like this. A points KL, tangent lines AP and AQ, the end of the sentence. So immediately without any hesitation, I just draw some additional conditions here. So I draw the tangent radii, I draw just the radii to the given points, I denote the equal segments, I denote right angles, I denote equal angles here. Actually, I would denote some more elements, but that is because of my experience in this in such problems. But for those who are less experienced in this particular picture, like this would be probably the minimum what to denote. Then let M be the midpoint of the segment PQ. Okay. So we consider PQ, we consider the midpoint M, and the midpoint here, sorry, what I didn't denote would be equal tangent segments AP and AQ, which I like, of course, perfectly knew at that moment. And from this point of view, that is some sort of must do. So we must denote that those are equal on the previous step of previous iteration of drawing process. So I have this isosceles triangle PAQ, in which I draw the midpoint of the base, the point M. So that is how I realize that I must draw this height by sector and like everything AM. Why? Just because it fits to the fits in the problem very well. It brings us the property of the point M, not just in the metrical way, so that the segments are equal, but also in the angular way, so that I can denote this right angle here. Also, probably I would draw at first that these angles are equal as well, in different color, or probably in also in different number of arcs comparing to this, so that I don't confuse. And also here I notice that the line looks like passing through the point O, the center. So I just do a double check, like intellectual double check, if it's true, if it's something I should expect. And if it's of course true, because we have this symmetrical situation in the angular bisector of the angle A, as the circle is inscribed into the angle. So I definitely understand that I should expect here this line, this bisector, being passing through both M and O. And probably I would be interested in these points X and Y sometime later. but still we continue drawing. So this is all I mention now is the process of drawing for me. That is exactly how I approach any geometrical problem. So I consider that I still haven't touched mathematics yet, geometry. I just recalled some properties, which is technically, of course, mathematics as well, but it's not like doing mathematics. It's just recalling related things in mathematics. It's not my inventions, right? Not something I noticed here, some new property. Okay, so let M be the midpoint of the segment PQ, the sentence ended. Prove that angle MKO equals to angle MLO. So we have this. Let's draw it in a different color, probably in blue. So we have these segments, and we should prove that angle MKO, this one, should be equal to MLO, which is this one, but I cannot just draw them being equal. So though it's almost invisible here, like I will denote them with similar but different notations in the terms of arcs. So we must prove that angle MLO equals to angle MKO. And I immediately start thinking about what does it mean geometrically? Is this property translatable to some other geometrical languages? And here, of course, we can notice that this is translatable to the property that KOML is cyclic. Which would be translatable to a number of more, probably more reasonable forms, right? So we must prove this statement in any form of the statement. So these points must be put to the same circle. Sort of that. Probably I will need a new picture here soon, but I will start from like denoting all these things. So now for me, geometry starts. Like now, process of some sort of search starts. So I can realize now that I have some angles already denoted, like some angles which I denoted previously, which would be related to. Oh, first of all, I noticed some angles which I didn't denote. So these angles would be equal to these angles, the purple arcs, just because of the right triangles, right? So these angles would be common, angle POA, for example. So this would be 90 degrees minus that angle, and this would be 90 degrees minus that angle. So I denote this. But also speaking of proving that these 4 points are cyclic or belong to the same circle, I can notice that these blue angles, which I drew previously, they may be of some use here because I can express the idea or the property of the 4 points being cyclic as this angle, this angle AOL, the external angle of, oh, sorry, AML, the external angle of M here, being equal to this, right? So if I prove that this angle is equal to this blue angle, then probably that will finish the solution. So is it true? And this is exactly in that paradigm of blue-red facts, right? So I search for the facts which would be red, like which would be provable, based on what we want proof in the problem, based on what we must prove in the problem. So it's in a sort a fact, right? So we believe with very high probability it would be true. But we cannot rely on that, right? We cannot use it so far. So we can ask this as a question. So is it true that AML equals to OKA, for example? So this is one of the potential strategies how to prove that. But also in general, maybe we should think also about the general statement, this KOML, which is geometrical, not algebraic, not about equality. So normally it would be more methods how to prove the geometrical statement. So if we think of this probably more general statement, KOML, is it possible to prove that this is cyclic? Then we may notice that there would be a different approach. So we probably may consider power of a point A here. So we know that the statement, like hopefully we know that the statement is equivalent to saying that AK times AL equals to AM times AO. So please let me know on chat probably, or like with personal message if you're more comfortable with that, especially those who will look this in recording. Like let me know if you know what is power of point, like the topic. Basically this would be very clear, like by definition implementation. So like this would be the question, but also if we speak, for example, about this, we may notice what? We may notice that like this would be actually very, very sort of popular or very famous property, that this would be equal to AQ squared. Why is that? Like that would be just property of a right triangle. So if we consider an auxiliary picture here, we have Q here, O here, M here, A here, and we have this similarity that A, M, Q is similar to triangle AQO, which is actually enough for establishing this equality. And this AK times AL, it would be just classically defined power of point A with respect to the circle, like this circle. So in particular, that would be equal to AQ just because of that. And here we have this equality. So like we definitely have this equality. It's just the same. So we resulted in just showing that this quadrilateral is cyclic. There may be many strategies, but like if drawing all these things and analyzing after doing all the preparations, analyzing what we need to prove, it actually brings us to very straightforward consideration. Any questions? Seems like no questions so far. Okay. What I wanted to discuss today would be related to like there are actually two topics which I wanted to discuss. But also I didn't plan to spend too much time on them because I wanted to go through some proofs and related ideas to that proofs. So I want to keep more basic in geometry, which we consider, which we use, and probably spend more time on the topics like cross-disciplinary topics like combinatorial geometry, number theory geometry, geometrical inequalities, which we probably start from the next class or next to the next class. And today I wanted to discuss today I wanted to discuss some aspects of homothety. So by definition, homothety is transformation of plane or not just plane, like of the space where we act, but normally that would be plane, which is defined by the center. So it would be oftentimes denoted with H of C and K, where C is point and K is a constant not equal to 0, maybe negative. So by definition, that would be mapping, transformation of plane, that is like function on the points of the plane. So if we have point C, if we have any other point A, then we must consider, like in order to get the image of the point, we must consider the following construction. We consider vector uh, CA. So image of the point A is defined by the following. It's equal to A prime, where this would be purple. No, this would be blue. Where CA prime equals to K times CA. These taken as vectors. So that actually explains how K may be negative, right? So for negative K, we have just two vectors, opposite in direction, but still uniquely defined by the length, or like uniquely related by the length. So we have that the homothety, like any homothety, is similarity transformation. Is a similarity transformation. Which means that homothety of any triangle ABC would be similar to triangle ABC. So if we consider the images of the points A prime, B prime, C prime, then the triangle A prime, B prime, C prime is always similar to ABC with coefficient of similarity K. Okay, what properties are well known about homothety? Like homothety preserves straight lines and directions. By directions here we understand the vector, which is directing which is along the line. Straight lines, circles, and centers. So these properties, I hope you heard. Like, first of all, let me know, please, write to the chat, please, if you are familiar with homothety, like if you used this before, or at least you heard, like, and actually like the level of proficiency, like you used it before, you just heard about it, you never heard about it, you used it like many times. So what is the situation? Okay, like that is actually what I expect. So you are familiar with the definitions, hopefully. Yeah, but probably used it not that many times. So the particular implementation of homothety, one of possible implementations, would be that in some particular situations, homothety just it shows it may serve more or less the same purposes as locus of point. So we have some condition, and we have, like, speaking of locus, that would be set of all possible positions. Speaking of homothety, sometimes we consider that as sort of description of some coincidence of positions in the term of possible positions of the object, not of a single point. So we may consider, like, there is a method of intersecting loci in geometry. So we take one locus, another locus, and we take intersection of the loci. Like, loci would be plural for locus, all right? So we take the intersection, and that is how we know the extensive list, like the explicit list of all possible positions for some point, like fulfilling all the conditions. For homothety, we may use it in some similar manner. So we may consider some trajectories of a figure, among which we choose some particular examples which are fulfilling other conditions. So some classical examples. There would be a very famous statement about three circles. So suppose we have three circles such that we can draw couples of common external tangent lines to them. So we have this couple, oh, sorry. We have another couple. And we have this couple. And they do intersect in corresponding points. So we have this point intersection. So let this would be omega 1, this would be omega 2, this would be omega 3. So we have intersection of such external tangent lines to these two being 0.3, for example. For circles 2 and 3, it would be 0.1, and for circle 1, circle 3, that would be 0.2. So the problem is showing that these 3 points are collinear, right? So that means that these 3 points, they belong to the same straight lines. P1, P2, P3 are collinear. There is some clever name for this statement, but in Russian it's famous as theorem of 3 like heads or shaped and like theorem of or lemma of 3 pointed heads. Do you know this statement? That is my first question. Is this statement familiar to you. Yes, no? Okay, so this would be related to what is known as composition of homotheties. So we have here three alike situations, and what we can say that homothety with center P1 and corresponding coefficient, say R2 over R3, would be such homothety which preserves, it preserves, like the claim would be following. It would be such homothety which brings, sends omega-3 to omega-2. So this would be claim. Why is that? It's because this homothety, it preserves these tangent lines as lines passing through P1. So and also it sends omega-3. Just one sec. Билли, перестань. Билли! Also, it sends omega-3 to some omega-3 prime, which is circle, and which is tangent to, like, let this be like L1 and L2, which is tangent to L1 prime, which is equal to L1, and L2 prime, which is equal to L2. So we say that homothety preserves just lines and circles. That is primary property, and also it preserves, like, it sends every point to some other point, right? So if we considered a tangent line to a circle, then after this transformation, the circle will go to some other circle, like not other, but will go to again to some circle, and the tangent line, goes also to some straight line, and still that circle, that new circle, and that new straight line, they must have just one common, like exactly one common point. They definitely have one common point because there was common point, and it will we will have an image of that point, but this image will belong both to that new straight position of straight line and new position of circle. So we probably should add here that it preserves intersections. Intersection points. No, intersections. Not it preserves not the points. Intersections, including tangency. So if we had intersection of two objects, then after this transformation, there will be some new shared point, right? So it would be also intersection. If there was tangency, then we will have the shared point, but we will have no new shared points or intersection points. Why? Because we just have the inverse transformation. We can reverse the operation, and it will be also homothety. It would be homothety with the same center, but the inverse coefficient. We can easily check that everything goes back then. So the new position of omega-3 would be tangent to the new positions of the tangency lines. But the new positions of tangency lines would be just the all positions of tangency lines. So omega-3 prime is inscribed to the same angle. But also it has radius R2 over R3 times R3, which is just R2. So it would be a circle which is inscribed in the same angle, which sends this circle to a tangent to another inscribed circle, which has the same radius as this circle. So it's just the circle itself. So that is how we show that this sends omega-3 to omega-2. The same we can say about corresponding homotheties in this point and in this point. So we will have the following combination. If we take the combination of these homotheties, so homothety with center P1, P1, coefficient R2 over R3. So it sends R3 to R2 to omega-3 to omega-2. Then homothety with center P3, which sends omega-2 to omega-1, would be written in a similar manner, like this. And there would be another homothety with center P2, sending omega-1 to omega-3. And this we denote as H. Then we have several statements. First, H is a homothety. Second, H has coefficient equal to 1. So it's homothety, like it's or there is actually an exception here, which I wouldn't write down, because it makes it less nice, the statement. Actually, there is a possibility that H would be a translation, parallel translation, just in the case if the coefficient of homothety becomes 1. But somehow it would be clear that this question arises just on the last step when we consider the entire composition H itself, but not on the intermediate steps. Of course, we need here all radii being different, all three radii. And 3, H preserves omega-3, in particular the center. So these are 3 properties to show, which actually would be showing that this is homothety. So H equals to identical transformation. And that would be what we need to show that. So the statement would be that then these 3 centers are collinear. And these would be parts of the home task. So these would be distributed into several problems. And that would be a full strategy how to prove such collinearity in different occasions. Yes, exactly. If it's identical, but like the question is if it's homothety or so. Yes, that is correct. So homothety or similarity, like translation, parallel translation. So actually here it would be more full to show that it would be similarity. Similarity preserving directions. So that is actually it for today. So I will then draw all these problems as like this. I will reformulate in the as a series of problems for home task, but basically that would be the strategy for proving many problems. And also that would be one of the primary implementations of homothety. Any questions? Like if you'll have any questions, any new questions, just feel free to write me on WhatsApp. But for today, that's it.
I just have a small question. Would homothety be related to circle inversion?
It would be actually related not much. It would have several similar motives and several similar pictures. Sometimes we can bring them to the same context, use both of them because they are very friendly to these tangent lines and circles, but otherwise they would be not very related to each other. Just somehow similar pictures, producing similar pictures. Sometimes. Okay.
I have a question.
Uh-huh.
If the resulting coefficient was not one, will it
Mhm.
be a homothety?
Of course, like if the coefficient is not one, then it definitely would be homothety, a proper homothety with the center with some coefficient which is countable by these coefficients, like by coefficients of the intermediate homotheties. But the only exception, possible exception, is when the resulting coefficient is one, the coefficient of similarity. Then it may be either homothety, and then so it has at least one uh, constant point, but then it is actually identical transformation, or it may be a parallel translation, parallel shift. It's also possible. Then it's not homothety because it has no constant points at all, no center of homothety. Okay,
Okay, thanks.
welcome. Okay, guys, see you next time. Bye.